will recap again this next week, towards the end of the week anyway. We'll go through all books, all on Friday, probably Thursday afternoon as well. We'll recap everything. Because my plan is to get everything finished by Thursday lunchtime at the latest, thereabouts. Bit of recap Thursday afternoon, full recap Friday of all the books, and give you as much questions as possible. Okay, make you ready for your exam, whenever your exam is. So, anybody got any questions at all for books 1 and 2? Or my new books 1 and 2, parts 1 and 2. Your old books are different. Or basically what we've covered this week. Again, if you don't make notes of certain parts you're maybe not quite sure of. Again, we'll recap stuff next week anyway, so don't worry. But please highlight any parts and hopefully get your new books by that point. Certainly for books 4 at least, because obviously not got new ones yet. Has anybody been told when they're getting the new books?
Nobody.
Nobody's told you yet. I'll chase up Sanjeev and say if they're trying to get you the new books, because it makes certainly revising a lot easier. The books are similar to what the old ones were. There's some new stuff in there, some old stuff taken out. So yeah, ideally it'd be better if you had the new books. You can most information is there, certainly the old books, but that should be sorted out. So I will chase Sanjeev up and try and get you. I've sent him an email with all the revision questions that are in the new books. So you should hopefully get them by start of the week with a bit of luck, at least if they don't get anything else done. Okay.
It would be better if you emailed us directly, because for email also we have to wait a long.
Right. Well, what to do, if you've all got my email, haven't you?
Yes, I have.
If you all email me individually, I can send you those back out, those questions. Okay, just do it after we finish tonight. If you all email me, I'll reply to your emails with those as well. Okay, and hopefully Sanjeev will print those out for you. But at least if they're on computer, you can look at them. Okay, so yeah, please feel free to email me once you finish the class today, and I'll reply to all those with a copy of all the questions that are in the book. Not a problem.
Okay, thank you.
Okay.
Okay, sir.
Right.
Thank you.
No problem. Any other questions you want to go through? I was going to start this probably after the next break, but we'll take it slow time. I'm trying not to go too far today in it, because at the end of the week we'll recap a lot of stuff that we cover in book 3 now in the morning on Monday. We should finish book 3 or easy by Tuesday afternoon, not a problem at all. And book 4 takes about 2 days as well, so Tuesday afternoon, Wednesday, Thursday-ish, thereabouts. So there's plenty of time for both books. So we'll take it nice and steady and do what we recap next week. Okay, if no questions, then what we'll do, we'll slowly go through part 3 and take it nice and steady and see how we get on. Okay, so we're getting there. So we're halfway there almost. We're just about to start next week. We're finishing books 1 and 2. So good division there. So hopefully that'll help you as well. Okay, so part 3 is gas turbine adaptations. We'll look at lots of bits and pieces there. Okay, good on me again. If you don't have my email, just in case, there's my email. For those that maybe don't have it, just take a quick note of it. And certainly email me, I'll ping you the questions, revision questions. Okay. I don't need that anymore. We've done all those. That's just the normal for the start of those. Right, contents. What we're looking at more in depthly is turboprop engines, general gas turbine engine control, overspeed safety devices, turbo shaft engines, which are pretty much similar to turboprops, reduction gearing. Again, we've touched this already in module 17, so it's a bit of a recap. We're sort of going back the way now, so some of this will be a bit more what we've seen already. Helicopter control systems. Why are we teaching helicopter control systems? Well, they have gas turbine engines, most of them. So you need to know a little bit of basic about helicopter control systems. APUs, I mentioned these quite a few times, but we're going to look at more in depth of these. What are they? They're just a very, very small gas turbine engine. That's all they are. Power plant for installation, flexible pipes, and a few bits and pieces thrown in between. So let's start off the good turboprop aircraft. Okay, basically what is it? It's a gas turbine engine with a big propeller stuck in the front. So what was the the comparison between that and the jet engine reference how much air. Was it a small amount of air, high velocity, a large amount of air, large velocity, or large amount of air, small velocity?
Large amount of air in a small velocity.
Yeah, that's pretty much it. So this poor little engine's got to work a little bit harder to get the power. Hence, remember, you can see here this example, we've got 1, 2, 3 stages of turbine. So remember, a turboprop engine tends to have more stages of turbine rotors to extract more energy to spin this big propeller. Okay, so we'll look at it a bit more in depth. So turboprop engines broadly split into 2 categories. You'll have, we mentioned them already, just a bit of recap, direct drive, fixed turbine, and your free power turbine, okay? Free power turbine. Remember, direct drive one, that is mechanically coupled to your HP spool, whereas your free turbine is just a shaft, a turbine, and a propeller. So it's free to rotate in its own environment. Yes, there is a reduction gearbox there to reduce the speed of the propeller compared to the turbine speed, but that's the only coupling it has. It isn't mechanically coupled to the engine. So there we go, direct drive, for example. This is like an old Dart engine, like the one we've got in the hangar. It just happens to have 2 centrifugal impellers. I'll just change my pen there. So the example here, we've got 2 centrifugal compressors, 1 big shaft, and a few turbine stages at the rear there. So it's just 1 shaft with 2 compressors, just this type of engine. That's just to show you an example. But the main thing is we have got a reduction gearbox to reduce the propeller speed. Now, on a free turbine, it's the same. We need a reduction gearbox because without a reduction gearbox, that propeller will spin far too fast because the shaft here is going to spin quite high revolutions. We don't need the propeller to spin because it's a lot bigger. Yeah. So imagine the tip speed. If that was rotating at the same speed of the shaft, it would just fly off and break into 1,000 pieces. Okay. And a little thing to take note of here is this little formula at the bottom. We've got shaft horsepower plus jet thrust equals equivalent shaft horsepower, ESHP. So make a note of that, highlight it, because they might ask you what is equivalent shaft horsepower. And that's basically the shaft horsepower plus jet thrust. We will break down horsepower into 4 components, but for the moment, just take a note of that, reference direct drive turbines. Okay, so equivalent shaft horsepower is the thrust of the engine plus the power from the shaft, the shaft horsepower. Again, we will break this down later, but just for the moment, just take a small highlight on there. Again, these are in your old books as well. It's still pretty much the same. I can't remember if that's book 2, book 3 in your old books. Okay, maybe book 4 actually. Turbine, as I described already, as you can see there, there's a turbine and there's a shaft. This one just shows you the shaft coming out towards the back, which will probably join to a gearbox and then go up the way to a rotor for a helicopter. But likewise, that shaft can go forward and connect to a reduction gearbox and a propeller. But the main thing is, it is not mechanically coupled to the main shaft within the engine. Okay, it's free to do what it wants. This example is just purely for a helicopter one, but the principle is exactly the same. Okay. Now, gas turbine controls, there are 4 requirements for all control systems, and they must be. Now, this is another acronym you can make up, an abbreviation. A for accurate. It has to be accurate in operation. In other words, no point in moving forward and then the thing goes backward. You know, it has to be accurate. So that's A for accurate in operation. So if we select something on, it must be on. It doesn't go off, etc. Next one is P for positive. Okay, positive in selection. So when we move a switch, we move control, it feels positive there. It actually goes where we actually tell it to go or move it. Okay, we switch the switch on, we feel the click. We move the throttle forward to maximum, it moves to maximum. Yeah, so positive in selection. So A for accurate, P for positive. Next one is R for reliable. It has to be reliable under all conditions in flight. No use going straight and level and that's it. When we're turning, we're pitching up, pitching down. It's got to be reliable under all conditions. What it's designed to do. And the last one is E. E for effective, regardless of the distance between the flight deck or the cockpit and where the engine is. And the reason we've mentioned that is because aircraft are different sizes. Some are quite huge, so the cockpit to the engine can be a lot distance away. Where a small engine, small aircraft, it's quite close. In olden days, we have the throttles. It's connected by cables, pulleys, turnbuckles, rods, etc. Well, it doesn't matter on the distance. When you move that from idle to fast to forward, it should be effective. It doesn't take half an hour to actually move the thing. Okay, so it doesn't matter on the distance where it's from. When you move your control, your switch, it is effective. Doesn't matter on the distance. Effective regardless of the distance between the cockpit and the actual engine. So you can imagine the olden ones where they've got ball bearings, connecting rods, a little bit of wear at one part can be exaggerated by the time it gets down to the engine. So that's why it's important when we do rigging that we take up all the slack and everything is in its correct position. So that's your 4 main requirements for all control systems: A, P, R, E. Accurate, positive, reliable, effective. Okay, and we'll go over that a few times with revision. Accurate in operation, positive in selection, reliable under all conditions in flight, and effective. It doesn't matter what the distance is, it's got to be effective. Okay. So again, a good one to highlight. A good chance we'll get a question exam on maybe 2 of those. They might give you a couple as an example and you have to fill in the rest in. So definitely know those ones. Okay, we've got a few levers and controls we'll have on there. I'll just get my picture up. I was going to try and show you. Where's it gone? Bear with me. Right, sorry. Yeah, there we are. Okay. Oh, that's gone off. Why is that going off now? There we are. Okay, it's working now. Okay, so in your levers we saw already, this one shows an example of a twin engine. Okay, so you got your left throttle, your right throttle, and your rollover levers here. So again, for thrust reverse, and things you might see is parking brake lights, parking brake levers, landing gear selection, trim, flaps, and all sorts of things. Doesn't matter what the control is, it's got to be able to actually work. Again, this is all on the quadrant, the middle part within the actual aircraft cockpit itself. A lot of these connections, the older ones, as I said before, they can be not fly-by-wire. The new ones are fly-by-wire, but a lot of them are still cables, rods, pulleys, teleflex cable, bounding cable. Again, we'll come across those depending on the aircraft type. Main cockpit separate lever selection. Again, like thrust reverse. Again, we need positive selection, so we'll go back to your main APRE scenario. It's got to do what it does, and irrespective of the distance, etc., and be positive. All good stuff. Possible the buttons. The levers themselves might have a button cocked to disengage auto throttle in emergency. We don't want the throttles doing their own thing. If you've got an emergency, we need to be able to disengage auto throttle. So again, some places will have facility for that. So main levers, we'll look at controls, HP cock, start lever, and we'll look at the LP cock. Mentioned these already, it's just a bit of recap. So the HPSOV, your high pressure shutoff valve in the engine fuel system, well, that switches the fuel on at the engine, not before, but at the engine. So before you open your throttles, you need to open the HP lever. That will allow fuel to flow ready for selection to your burners. And it might have 3 positions. You have fuel cutoff, start position, there's a prime effect, and a run position. Okay, so it could potentially have 3 positions. So basically, normally just 2 on and off, but it might have 3. So fuel shut off, cut off, start, and run. Okay, depends on the aircraft itself. There we go. All right. LP cock, again, we'll come on to that in a minute. Again, what we meant before was LP cock supplies the fuel from the aircraft side via your ball cock, which is a 90-degree turn valve. Okay, that's always left on, apart from the two occasions mentioned before, is emergency and maintenance. Within the levers, your throttle levers, again, your integrated throttle levers and that sort of thing, you might have your thrust reverse. Okay, some are rollover levers like we saw already. Some are integrated, some are single operation, some are double. It all depends on the aircraft. That's just showing you a diagram of positions of rollover levers. Again, don't worry too much about that one for the moment. Just a basic insight, not the best diagram. But there's a better one like you saw already. Again, HP cocks, there's your 4 throttles. Again, you can just see at the front there, there's the rollover levers. Okay, so when the throttles come back to idle, you can pick these one up the front, lift them over and select thrust reverse, and then you can push back up on the throttles to a drop about 50% if required. Okay, a couple of examples, we show that by Boeing use a cam track and some other aircraft use a different version. You probably see there, well, wait a minute, we've got handles there, we've got handles there and handles there. Well, the reason we've got handles there is initially when you start pushing up the throttles to go to maximum, rather than have your hand away up here, you can put it up, and then obviously if you're bringing back, these will be at different angles. So it gives a better control at different positions of the actual throttle itself, which is always a good thing. Again, it all depends, as I say, on the type of aircraft. Throttle levers, there's one we've got. This is probably a turboprop aircraft. The reason being, we've got this colour here. What range do you think that might be called? Where my laser is. So we've got maximum, idle, and then we've got this range here.
Beta range.
Yeah, that's a beta range.
Beta range.
So this is a turboprop aircraft. Okay, we've got selection there, so we can bring an integrated throttle lever, connect to your propeller control lever, come back to idle, and then we get a positive selection, so we feel a click, comes back down into the beta range and back into your plus 20 to your minus 20 degrees for throttle. Okay, and this is sort of version you might come across, not in this one, but certainly on different aircraft. This diagram here shows you the position of the cam track. Okay, and if I remember right, I'll just double check. Have we got it for forward? No, that's the size of the one I've got at the moment. What I'll do, I'll try and enlarge that photograph for you to make it a bit easier to see, just in a minute. So the different versions, what you want to look at here, there's your main throttle arm, there's your thrust reverse rollover lever, okay, which can only be operated when the thrust reverse lever is back at idle. Now, this part here, we're in the forward idle throttle position, so we can actually engage thrust position, reverse thrust, because it's in idle. This little lever here has got a little ball bearing on there and a little ball bearing on there. Well, that's free to rock. And the reason it's free to rock is there's a cutout in this part. So what I'm going to do, I'm just going to enlarge this diagram. Just bear with me 2 seconds. I can get to work. Just make it a little bit bigger for you to see. Leave this one out of the way at the moment. Maybe that make it a bit easier. Okay, in fact, I'll lift it up a bit more. Bring it down. I'll come to the bottom bit in a minute. Okay, so let's move this out of the way. Right, I hope that's a bit easier to see. You can see here, it's like a seesaw. Okay, there's a little pivot point here. All right, so when your normal throttle movement, this bar here stays where it is. Okay, the throttle moves up and back, up and down the hill, if you want to call it that. Because there's an indentation or cutout, this rocking lever can actually locate into there. So when we lift up the thrust reverse lever, that engages the front part, lifts it up, locks it into there, so now we can push the whole throttle forward. When we're in full throttle position, we can't select thrust reverse, because if I try to lift that lever up, it can't pivot this lever here. There's no indentation, so it can only go into this hole once it's back at idle. All right, let's move this up a bit more to the next part. So in the reverse idle position, Okay, you see it is in location. We can lift the throttle up, it will engage, and then we can move the whole throttle assembly because that has now engaged in the throttle assembly itself. So it is free to actually move the throttle. We can move it into 50% range if required. All right. I'd like to get an animation for that. It's a bit dry, unfortunately. I'll come back to that one further. So turboprops, single lever control. Yeah, it takes a lot of load off the pilot. So turboprop engines of direct drive or a fixed turbine type will be fitted with a single power lever. So this power lever is actually connected to the propeller control unit. So instead of having two separate levers of your engine power and your propeller control, this one does it all for you. So it takes the load off the pilot. So both the fuel control unit on the engine and the propeller control unit on the PCU, your propeller control unit, are interconnected by one simple throttle. This one has obviously got two engines to an engine. So just by using one engine throttle, it's connected to your propeller control unit, which controls the angle or the pitch of the blade to control the speed of the engine. Remember, if the engine's going too fast, the propeller control unit will coarsen off the blade to cause more drag in effect, which will slow the engine down. So they both work together, nice and easy, one lever, one action. Okay, so it tends to be for a fixed turbine one now. Control connection with HP cork also ensures that the fuel flow to the burners is shut off before the propeller is feathered. Okay, so basically you pull this lever back, shuts the fuel off, and then once the fuel shut off, then that's great. Then it will go into the feather position. There's no point to go into feather position before shutting fuel off, because that means it's going to slow down too much, and if you've still got fuel going in, there's potential for an engine fire. So we must make sure that we shut the fuel off first before we go into a standard feather position. So that prevents the engine from overheating to try and supply power to the blades in the feather position, which we don't want. We don't want that engine spinning, okay? Especially on a fixed turbine one. Dual lever controls. So instead of the one lever to do both the fuel pump and the propeller control unit, we're back to twin levers. Sometimes the propeller control lever is called the condition lever. So just another name for it. So normally used on engines with a free turbine. So this time you've got the power for the engine, and you've got to also manually select the pitch of the propeller as well. So single lever, fixed turbine, dual levers for free turbines. Okay, so power lever and your prop control lever as well. Okay, power lever. Okay, on this side, that's the one that will go into your beta range. Okay, beta control. Remember, you can go back into idle, back into beta range as well. And you can sort out all your other bits and pieces too. What else? Let's move. Sees that. So a power lever schedules fuel flow from idle to takeoff, arranged by positioning the operating lever on the fuel control unit, FCU. When you bring it backwards or rearward selection is made from idle to reverse, it schedules not only the fuel but also the blade angle, okay, from degrees to -20, just like we saw in module 17. So we're recapping what you've been taught now before module 17. All right, so that's your power lever. Again, remember that range is also called the beta range. Your PCU, your prop control lever, also known as your condition lever over here, connected directly to PCU and selects the required RPM by applying or releasing pressure on the governor control spring. Remember, go back to module 17, the governor will go up or down accordingly, which will increase or decrease the pitch, again depending if it's a single acting propeller or a double acting propeller. Okay, remember, single acting had a big spring and oil pressure one side, and the double acting had oil pressure both sides. So it depends what system. So the governor will control that. Remember, on speed, under speed, and that sort of thing that we spoke about in Module 17. Operates when the propeller is in normal constant speed range, but does not influence propeller blade angle while the propeller is operating through the beta range. So that's controlled by the power lever. Feathering, fuel shutoff is selected by moving this control through the rear. So what you're going to do is you will move your power lever back to idle, and then you bring your condition levers back, and that will shut the fuel off. Okay. Safety devices. We've got various types of safety devices for overspeeding. Automatic, mechanical. Well, we know about the mechanical side already, don't we? Some of the governors and that sort of thing. And mechanical, this is a different type of governor. And if I've got my animation to work right, it's not the best, but it gives you an idea of how this operates. So what we've got, I think we mentioned before in Module 17, you have a drive shaft. Now, the faster the gearbox is going, the faster these weights are flying round. And the faster they fly out, then these will tip down. So these, remember, look like birds' beaks. So the weight will fly out the way, which will push this down. Well, if that pushes that down, that restricts the servo flow, the servo outlet, which will then obviously decrease the amount of fuel pressure. Okay. There we go. There's my best animation. I can try and get to make it work for you. So we're going faster. It goes fast until the weights fly out, pushes down on the valve. That restricts the amount of flow there. So it's going so fast, so we need to slow down a little bit. Okay, so that'll reduce the servo pressure. Okay. That was included. That's an older version, just a sort of older version taken from a Dart engine. Nothing too much there. Electrical. Well, we've got electrical like what we call a phonic wheel, where you have a magnet with an electrical sensor on it, and every time a tooth goes past it, will induce a pulse, and we end up with what's called like a sine wave, again you've seen from Module 3. And that pulse will be picked up, well, the frequency will increase or decrease depending on how fast that gear, which is on the shaft, is going round. Okay, so the faster it's going, the more intense the frequency, and that will be amplified through an amplifier to a signal to your fuel control unit and to your RPM gauge as well. If it gets too fast, it will send a signal to the governor and shut down the fuel supply. The other emergency system we've got is what's called the LP shaft disconnect system. Never been used before. Well, it's been fitted to many aircraft engines. It's never actually had to be activated. It's a very simple procedure. Okay, and what you've got there is on the LP shaft itself, there's a big nut. Now, normally that'll be spinning fine, but if that nut or the shaft breaks, that will stop. The nut will continue to turn for approximately 3/4 of a turn, and what it will do, it will push against this lever. We call it a bell crank lever. So it's on a pivot here. It looks like an L shape, it will move like that. Okay, the nut will spin out, push this lever, which will pull on this cable. Well, that cable is joined all the way down. So actually here it is here, it's exploded view. All the way down the side of the engine, inside the engine. Then it comes out of the engine, and then it goes down to your HP cock lever, okay, on the engine side. That will then disconnect your HP SOV. So it will shut off your basic HP cock on your engine. So it doesn't matter what the pilot does in the cockpit with the HP cock, it will mechanically have disconnected here, and that will be it. It will shut the fuel off. Again, this is on an old SPA engine. There are various different engines that have them, and as far as I'm aware, it's never had to be activated. They've never had a broken spool, which is quite good. Okay, but just a simple cable all the way down through a couple of pulleys, and eventually to a split system. So this lever here, it's on like a little ball, so it cracks open. Yeah, so you can just see the little ball in here. Little pin will crack open, split the lever, and it will stay in that position until it gets reset. So a good automatic mechanical thing. The thing to remember here is it only takes 3/4 of a turn, not a full turn, just 3/4 of a turn to actually move again. So you can imagine that'd be quite quick. 3/4 of a turn, done, push the lever, pull the cable. So again, this cable would have to be rigged as well, because they don't want it too slack, they don't want it too tight. So in the event if there was a failure, it would disconnect at the appropriate time. It wouldn't take too long, or it wouldn't happen too quick either. Okay. So very, very important there. Alrighty. Let's see. We'll go back on that one once I've covered that. Okay. It's actually overspeed devices there, the basic ones. I can't remember if I put it on the next slide or not. Yeah, electronic system is an input into the FAFC. So you've got an electronic version of this one. So remember, what was FAFC? It was a full authority fuel control. Only controls the fuel side. Again, it will get a signal from the phonic wheel. Instead of a mechanical lever like we just saw there, the electronic side uses a speed signal and on the LP compressor, or indeed the fan, and another on the LP turbine. So if you get a mismatch in direction, because if the LP turbine and LP fan are rotating differently, well, something's broken, the shaft's broken. So if it senses a different position from the two sensors, it will go, wait a minute, that's not right, shut the fuel down, something's gone wrong. Okay. The shaft shear, then the turbine will immediately produce a faster RPM signal than it would be at the front and the compressor unit, so you get a different signal. The FAF will recognise that difference and operate what's called your PRSODV, your pressure raising shut-off and dump valve, and that will shut down the engine. Right, so slightly different on the FADEC version compared to the mechanical version. But the main thing is, it does the same job. Okay. All right, folks, that's what, 3:10. I think we'll go for another break. We'll recap a little bit already. I won't go too far with it, because it's not a last stretch before the big weekend, the big holiday. Right, let's see. Okay, look. So we finished off on LP disconnect shaft system. Okay, just a mechanical version. And likewise, with electrical version, we had the FADEC control looking at phonic wheel type sensors. Again, we'll cover phonic wheels a bit more in depth later on. Last part of the day I'm going to look at is how we join shafts together, like turbines to the shaft to the compressors, and so on. So I'm looking at what's called 3 types or common couplings used within gas turbines. Okay. The first one is a curvic coupling. The second one is called a gimbal, and the third one is called splined. And I'll show you some examples of each of those. So 3 ones you want to remember: curvic, gimbal, and splined. First one is a curvic one. Oops, move that there. Now what it is, it's a set of teeth, a set of male and female teeth that join together. So once they get squashed together, the male goes into female, and then we can squash them together. Okay. Now that's represented here. Now this little zigzaggy lines here, well, that's the teeth on the coupling, which will mate onto the disc. So the same sort of teeth there. So again, depending on how many items you've got to fit, it all goes on a shaft. They slide on together, and then you'll have a shoulder shaft and some sort of nut that tightens it all up together and squashes them all into line. And that's all the thing that's holding them on. So instead of having lots and lots of bolts and nuts, you just put these teeth together, one end of the shaft will have a nut on it, squash it all together, and that will keep them there until whenever. So that way you can disconnect the shaft, when the shaft's out of the engine, undo the nut, slide each component off, and replace as appropriately. So there's a coupling there, there's another coupling there, there's another coupling there, and so on, so on, and so on. Okay. Again, the shaft will be in a bearing, so we call it curvic. Think of curvic couplings as a curved joint. It looks like a set of teeth. So curved teeth, that's the way I sort of remember it. Curvic coupling. Okay, rows of teeth there. Next one sounds like a dumbbell. I call it's a gimbal. It sounds like a dumbbell because of the shape of it. It's a very lightweight hollow piece of tube. You must handle these with care. They don't weigh a lot, but they're easily damaged. They are basically a steel shaft with flexible diaphragms at the end. Now this one's showing you it's been cut in half just to show you what's inside, but also it'd be like this, completely round. You'll have a flange connection each side, usually maybe 3 or 4 bolts to connect to a gearbox, and one side to gearbox and one side to the engine. All right, it's commonly known as PTO shafts or power takeoff shafts. And these flexible joints here allow for a little bit of misalignment. When you're putting it on to expansion, it allows for a little bit of misalignment. So you can actually bend these flexible joints a little bit, okay? Some have a sliding type joint as well, where the ones we stuff on, they have an internal shaft within a shaft, so you slide in position, and then I call it, its official name is a gimbal. All right. So you can see here, you've got a connection to the main gearbox, and you've got a connection to the engine, and a slight misalignment. So by having these flexible joints, it allows for slight misalignment. Very importantly on these is this black protective paint that's outside. If you drop it and you scratch it with a tool, do not fit it. Very, very important. It has to go back and gets treated with special paint and also checked for potential cracks. Because it's quite thin, the last thing you want is either an engine spinning so fast that there's a crack in there, that comes off, it splits, it's just like a piece of ammunition, okay? It will trash the jet. So they will come in a special box. You only take them out when you're ready to fit, and likewise, when you take the old one out, even though the old one is maybe getting taken out for checks because it's been in for so many hours, it will have a log card, it will have a serial number and that sort of thing. Handle it with care and then replace it with the one in the box. Make a note of it. Okay, so please handle. They're not heavy at all. As you can see, they're hollow inside, but they don't just put any paint on there. It will go back to get special treatment, anti-corrosive paint, and then a top layer of paint and probably some lacquer on top. All purpose made for that type of connection. And the last one is a spline one, typical sort of connection you'll see. Again, I'll use my car scenario. That could be a drive shaft on your car. Okay, fuel pumps, hydraulic pumps, etc. will have splined, male splines on one end, female sector on another one, and that's your typical one. So splined sounds like spine, splined. Okay, so it's the 3 main types: your curvic, your gimbal, and your splined type. All right, the main sort of connections. Male side into female side. All right. Along with that, some of the couplings, you might have what's called anti-vibration couplings. These are sets of very, very, very thin washers. Depending on how much they need, it depends on the gap. Now, by having these separated washers, very thin, they put together, they absorb any vibration. So they use them as anti-vibration couplings. Okay, and they'll be sat in here, bolted together, okay, with an adapter. And they're just very, very thin washers, all laid up. You might have maybe 6 to 10 of them, possibly. And you usually call them red, and that's why I've called them in here as being sort of red. Laminated steel disc coupling, all right? It just helps prevent any vibration possible. Okay. All right, so that's as far as I'm going to take that today. What I'm going to do now is just go back on what we've just covered, the small part I've just covered now. Any other questions, and then make sure you've all emailed me for the questions for book 2. Sorry, the questions for all of module 15, not just book 2, and I'll send them back out to you. And hopefully Sanjeev will print them out to you. He might email you. If he emails them, fine, but at least, as you say, if I email them, you'll have them anyway ready to go. Okay, so we'll just go back away. So as we've heard there, that was the last one. So that's your anti-vibration coupling. As it sounds, it prevents anti-vibration. Your spline coupling, male, female splines on the axis of the shaft. You might have a locking ring in there depending on what's going on. Again, some of these connections, you can actually take them out. Okay, the wasted shafts are designed to snap, rather the components snap than the gearbox. It's obviously harder to change the gearbox. So some of these wasted splines will be designed to snap if, say for example, this pump seized. Well, if the pump seized and the gearbox is spinning, it'll snap the shaft, that's fine. We can replace that, we can replace the pump, but we don't want to break the gearbox. The anti-vibrations, I say, we've done that one. The gimbal, again, power takeoff shaft. You might see these in farm type tractors. Tractors have them for their ploughs and whatever else. Anything that has a rotation on it, you might have seen those sort of things as well. But as I say, just a set of mated teeth, squashed together, interconnecting, and it's a nut at the end of the shaft holds it together. Nothing drastic there. There's your 3 curvic, gimbal, and splined. So, okay, going back away then, we had the mechanical and electrical method of LP disconnect system. How did the electrical one work? Anybody? What was the basic principle behind the electric one?
Phonic wheel?
Yeah, phonic wheel, yeah. So the turbine and the compressor spinning obviously together on the shaft, but if that shaft breaks, then the turbine's going to go faster than the compressor. So by the difference in the wheel position, the FADEC will recognise this and go, that's not right, something's wrong. They should be together at the same time. That will shut the wheel off through what was called your PRS ODV. Okay. The mechanical version, go back to the diagram. Okay, simple lever on a nut on the shaft. But should the shaft break, it will go quicker. It will disengage by 3/4 of a turn. Okay, push on a lever, which is called a bell crank. That will pull the lever, and then that will pull the shut-off valve relay on that arm there. Okay, that connection will go to the cockpit for the HPA cock in the cockpit. That lever goes to the actual shut-off valve on the engine. Okay, that will actually disconnect when the cable pulls it. So it doesn't matter, as I say, what the pilot does, it will not open it. Okay, I said in all career I worked on those, it never got activated once. They never had a broken shaft. So it was well designed, very well designed. What was the other mechanical type overspeed protection system we've got, which we covered in the fuel system?
Governor control.
Yeah, governor control. We'll go back to that one. There's that one. So nice and simple. It was just a case of the flyweights. Okay, as the flyweights there, these ones here look like a bird's head. As they get more centrifugal force, the force going faster spins them out. So as these weights here at the bottom fly out the way, then the top of them comes down, pushes down on the valve, and the valve restricts the servo flow. Okay, so we get a reduced pressure here, which means reduced pressure, reduced output on the pump. And then when it all settles down, when it slows down, the spring pressure here will push that back up in accordance with the heads coming back to normal position with less centrifugal force, which will bring the valve up and allow servo. Turbine or free turbine? Dual lever controls with fixed turbine props or free turbine props usually.
Free turbine?
Yeah, free turbine. Yeah, nice free turbine. So we've got your power levers. We'll go back to the big diagram. So your power lever, which is for your engine control, all right, and also your reverse thrust range, your beta range, and then your propeller control levers, or your sometimes called condition levers. We'll also, once it's in the normal constant speed range, that can control the pitch of the blades for coarse or fine, etc. But you can also shut the engine down. So we bring these to idle, and then bring these back, and through a gate that will shut down the fuel as well. And always a safety, it always shuts the fuel off first. Oh, excuse me. It shuts the fuel first before it goes into the further position, because we don't want fuel to be in the combustion chamber and then start spinning the propeller when it's in the further position. Okay, so before that, with the single control, single lever, again, tends to be on the free turbine, the fixed turbine. The dual one was on the free turbine, sorry, I beg your pardon. Okay, so the single lever, that was interconnected with what? So the single lever was also connected with what other control? So the FCU and also the, what was it connected to? So one lever did both things, unlike the dual lever one. So what was that?
FCU and PCU.
Yeah, repair control unit. Yeah, like on the free turbine one, you've got individual movement, but certainly a fixed turbine, you want it direct control, so it takes load off the pilot as well. Okay, and I'll just move that back down. Okay, so that was your reverse thrust. On your throttle levers, again, there's a row of levers. Okay, so remember, this cam, this rocking arm can only be activated when the lever is back at idle because of the indent in the back. So the little cam can roll into there, which allows the lever to be lifted up. So anywhere above idle, you physically cannot lift the roll of the lever up because the little rocking arm cannot sit into that gap at the back. So once you're at idle, then physically, yes, you can. And then once you lock in position, you can roll it over, that locks it down, and then you can push the forward thrust assembly up to about 50%, including reverse thrust. Okay, so nothing too bad there. Okay, if you're in beta control, just to recap on module 17 a little bit, if you're going to beta range, the unit, the reduction gives like oil pressure to find the blade below flight fine position, where she'll go into ground fine position, and then obviously further decreasing angle as required for reverse thrust.
We'll go through ground fine bits.
Yeah, so flight fine, ground fine, beta range. Yeah. Again, like we saw in module 17. Okay, the two examples I've got in the book is Boeing adapt a rotating cam, okay, where Airbus have got a simple rocker method like the one we saw in the diagram there. Again, they're just examples, we don't take them word for word. But again, the main thing is it can only be activated when it is at idle. The HP cock, HPSOV, has potentially normally two positions, open and closed, but it can also have three positions. What were the three positions?
Fuel cutoff, start position, run.
And run, good, yeah. And LP cock, what was the purpose of LP cock again?
Fuel flow to burner, indirect.
Not to the burner, it's, yeah, prevents, remember, you can use LP cock for two positions only, or two occasions, which were? I've covered that in the fuel systems previously. So there's two times you would operate the LP cock. Normally it's left open all the time, but there's two times when you might want to shut it.
Fuel cutoff, fuel on.
No, just two occasions. Normally you wouldn't touch this at all. You would just leave it open. Okay, it's your HP cock is your fuel to the engine, but the LP cock is the fuel from the aircraft to the engine. So normally leave it open, so the fuel supply is always ready for the engine. But there's two times when we actually switch it off. Which were what? We covered it in book 2. When would you want to switch or prevent fuel from coming out the aircraft? Two main times. Let's say you're doing an engine change.
Is it mechanically and electrically?
No, yeah, it's mechanical and electric, but when would you want to switch them off? Not how you switch them off, when would you want to switch them off?
During maintenance.
That's it, yeah, maintenance and?
Maintenance purpose.
And what else? So maintenance, if you want to remove an engine, we don't need to defuel the aircraft, but also when there is a emergency. Yeah, we want to cut off the supply of the fuel to the engine very quickly. We can shut the LP cock, so there's no more fuel going to the engine. So even if you've got the HP cock open, it doesn't matter. You've shut the fuel off, get inside. Emergency and maintenance purposes. Okay. All right. the main one, right? Who can tell me the 4 requirements for all control systems? What are the 4 requirements for all control systems? An acronym is APRE. A-P-R-E.
APRE.
Yeah. So what does A stand for?
Accurate.
Accurate. Yeah. In
Positive
operation.
selection.
Positive selection. Yeah.
Reliable under all conditions of flight.
Yeah.
Effective.
And effective.
Good stuff. Yeah. Okay. What I have it on the PowerPoint, I'll just add from the book here. It says it should be remembered that aircraft fly in different conditions. So hot climate, cold climate. So you might take off in a cold climate, you might go in a hot climate, or likewise, you might go from a hot climate to a cold climate. And also you've got expansion, contraction controls. So hence why the controls have to be set properly to allow for that. Okay. For example, they can be taken off from Middle East, experience ambient temperatures of 50 degrees C and upwards, and then climb to altitude where it's minus 50 odd. Okay, that will impose a great strain on controls. So there should be no slack in the hot weather as to render it inaccurate, because it could stretch, and not so tight as in cold weather. It'll make it even tighter, you know. So they've got to be just perfect. Outer engine control, so 4-engine aircraft must equally as easy move as the inboard control. So it doesn't matter what controls you've got, they've all got to move the same amount, especially like we've got here in a 4-engine control. The same amount of pressure for each and the same amount of effort, and all be accurate, positive, reliable and effective. Okay. Then back to good old direct drive turbines and free turbines. What was the difference between the two again?
In free turbine is not mechanically coupled.
Yeah, that's fine. So, and the fixed turbine was obviously mechanically coupled, yeah. So when we're starting these engines up, which we'll cover later on, you can start a free turbine in any position of propeller position. Yeah, it can be fine, it can be fixed, feathered. It doesn't matter because there's no mechanical strain on the starter. When a fixed turbine, it's important that you start the propeller in the fine position so it cuts through the air nice and easily. If you have it full on, it's trying to swim through the air, that's a lot of pressure or strain onto the engine. That puts strain onto the starter motor and overstress it. Okay, so very good. And what was equivalent shaft horsepower, or ESHP? What was that a combination of? Equivalent shaft horsepower. There was 2 things added together that make equivalent shaft horsepower.
It's shaft horsepower and jet thrust.
Yeah, good. Shaft horsepower and jet thrust. That gives you equivalent shaft horsepower. And as I said, we're going to look in later on at the different types of horsepower, from indicated horsepower, brake horsepower, shaft horsepower, and that sort of thing, what the difference is between the 3. And again, you could possibly be asked a question on those as well. Okay, let's double check if there's anything else we could go through before we finish. We've covered most of that. That's done. Single lever, dual lever, yeah. You're all good with beta range, not a problem at all. And as I saw before, we can have control locks on the quadrant to help prevent control flutter or vibration, okay, and control creep, just in case. Again, so we can, especially if there's wind. If you've got a fixed turbine or that sort of thing, it can vibrate. So we need to stop controls locking and moving about. All right, that's fine. So there. Done as far as good. I'm not going to go any further with that today because that leaves us a good point. Next week on Monday, we'll start off with turbo shaft engines.